Good morning. This is Siddhartha Borkotoky from IIT Bhubaneswar. In this talk, we are going to discuss about a modulation technique known as the Chirp spread spectrum technique. We will discuss how Chirp spread spectrum works, how are the modulations and demodulation done, and what are its implications in the context of the Internet of Things or IoT, in which it has found a lot of use in the recent past. Since this is a FDP, I will assume some basic background in wireless communications on the part of the audience. However, my goal is to keep things very simple and discuss mostly the basics without going into certain intricate details. So I hope you'll find this talk interesting. So to motivate the use of Chirp spread spectrum, or CSS as we often call it, in the Internet of Things, let us first take a step back and discuss what are the typical communications requirement in IoT. So oftentimes, as opposed to cellular communications, in IoT, we have low power nodes or end devices that transmit small amounts of information. Unlike audio or video, which involves long streams of large amounts of data, instead we often have small amounts of information, such as sensor data, where something is sensed and then transmitted infrequently. So we have small amounts of information that are sent relatively infrequently. So these are the typical requirements of most of the IoT applications. We have a bunch of low power sensor nodes sensing physical parameters, which results in small amounts of information, typically a few bytes at a time. And these information also are transmitted relatively infrequently, maybe every few seconds or maybe every few minutes up to every few hours. So what are the challenges in such communications? Here the challenge is not about having a great data rate like we try to achieve through the use of MIMO and OFDM, etc. in cellular communications. As opposed to that, what we want is we want to transmit with as little power as possible, so that our end devices or EDs, which are battery powered sensor nodes, work for a long time. So that is our main requirement. Now, given that requirement, what we need are modulation techniques that provide reliable communications over the desired range. By desired range, what I mean is that depending on the application, we might want different transmission ranges. For example, if it is a industrial IoT application where we are trying to measure certain industry parameters such as a conveyor belt rotation, some fluid transmission, air pressure, etc., over a factory floor, for example, then my desired range might be a few meters or a few hundred meters. On the other hand, if I am looking at a smart city IoT application or a smart agriculture IoT application, then I have sensors installed over a relatively large geographic area that might span up to a few kilometers. And we want to transmit information over that desired range. And such transmission ideally is such that we have certain sensors distributed over an area, and they will all transmit to a gateway. So they all transmit to a gateway without the use of any intermediate devices. This is the standard model for IoT data collection, and it is the simplest possible model. So what we want are modulation techniques that would provide communication from point A to point B with an acceptably low packet error probability, which is what we mean by reliability. And that must be achieved without spending a lot of power, because as we all know from communication theory, if we increase the power, then of course we can get reliable communications as long as certain other conditions are fulfilled. For example, we are ignoring interference in that particular statement, but in the absence of interference or in the absence of any such other parameter, power dependent parameter, or power dependent artifacts, I'm sorry, increasing the transmission power will increase the reliability. However, increasing the transmission power will also increase the draining of the battery at the low power nodes. So this low power is the keyword here. So we want to have low power nodes transmitting at relatively small power levels, yet achieving long ranges or the long ranges of smart city or agricultural IoT applications. And this is what has led to the emergence of a particular class of communication technology known as the low power wide area networks, also called LPWANs. So there are quite a few LPWAN technologies in the current market. Some of the most prominent names include a technology known as LoRa, which is the short form for long range. It is marketed by a company known as the Samtec Corporation, which is an USA-based company. Another technology is known as Sigfox. Yet another one is Ingenu. So there are many such techniques, but of these, this LoRa technique LoRa technology has come to become one of the most widely adopted technology in the LPWAN world. So the claim of LoRa, or what LoRa has demonstrated so far, is an ability to transmit over several kilometers of distances. So for example, if we are looking at a smart city application, we may have LoRa end devices, LoRa sensor nodes, transmitting from certain areas in the city to a gateway located several kilometers, perhaps 2 to 10 kilometers away, directly from the sensor to the gateway. So that is the power of the LoRa technology, and LoRa does it with a fairly low power consumption at the sensors. Similar transmission ranges are provided by Sigfox Ingenu as well, but in the case of Sigfox, the amount of data that can be transmitted is relatively or significantly lower than LoRa. And Ingenu, for certain reasons, it has not caught up that much yet with the other two technologies, namely Sigfox and LoRa. So coming to LoRa one, so we will restrict attention to LoRa in this talk. So in LoRa, this LoRa term refers to the physical layer of the communication, and a MAC layer built on top of the LoRa physical layer is known as the LoRaWAN. And the physical layer LoRa uses a modulation known as the Chirp spread spectrum. Yes. So this Chirp spread spectrum is the secret behind LoRa's long transmission ranges at low power consumption. And this is why this is the reason behind Chirp spread spectrum's popularity these days is the fact that it is used by one of the most prominent LPWAN technology in the current market. And this is what motivates our discussion as well. So clearly in the name Chirp spread spectrum, there are two components. One is the spread spectrum part. So like in any other spread spectrum technique, for example, direct sequence spread spectrum or frequency hopping spread spectrum, here in Chirp spread spectrum as well, we have a widening of the spectrum. We will transmit over a frequency band that is wide compared to the rate at which the symbols are transmitted. The other part of CSS is the chirp. Chirp is a specific type of signal in this context that we will discuss in a little while. But because of its properties, this chirp combined with spread spectrum, what we have is a type of signal waveforms that are quite resistant to fading. So they are resistant to multipath propagation and Doppler shift and consequently to different types of fading. And what that means is that when we use CSS, we have receivers with rather low sensitivity. So the sensitivity of a receiver determines how weak a signal it can successfully receive. So if we have a receiver with low sensitivity, that receiver can work in an environment where the received signal has been attenuated to a great deal due to fading as well as due to path loss. Since we are transmitting over a long distance, we will definitely have a large amounts of path loss. So such path loss combined with the fading, of course, will result in a very small powered signal, very weak signal reaching the intended receiver. Yet, due to the spread spectrum techniques, chirp spread spectrum techniques, physical characteristics, there is a greater probability compared to other modulation techniques that the receiver will be correctly demodulating the received weak signal. Let us now be a bit more specific and look at how the CSS modulation works. So CSS is essentially a M-ary orthogonal modulation. So this means that we have M modulation symbols. And they are all orthogonal to one another. Now, what are these symbols? Each of these symbols is called a chirp. It is a chirp. And how does a chirp look like? A chirp essentially is a sinusoid whose frequency varies with time. So a typical chirp might be starting with a certain frequency, and its frequency gradually increases. Or maybe a chirp can start with a very high frequency and slowly its frequency decreases. So a chirp looks something like this. Since the frequency of the chirp signal is changing over time, we now have to define something called the instantaneous frequency. Just like in a frequency modulation scheme. So at any given point in time, the frequency is called the instantaneous frequency of the CSS signal. Now, let us try to relate how the instantaneous frequency might vary over time. So let us suppose that we have a CSS signal with bandwidth given by BW and a center frequency FC. So we are looking at a spectrum maybe like this. We have a center frequency, we have FC minus BW by 2 and FC plus BW by 2. Now, given this information, how will a chirp look like? So any given chirp will start with some starting frequency. Let's call it Fi. So the chirp, as it starts, it will have certain frequency. So at the very beginning, we have Fi as the starting frequency. Then the frequency of the chirp will increase from Fi until it reaches a maximum frequency of Fc plus Bw by 2. At that point, so for example, let's draw it here. We finally reach the maximum Fc plus Bw by 2. I'm sorry about the drawing. It should have been symmetric over the with respect to the horizontal axis, and the frequency should have been increasing linearly, neither of which is true in my case. But in any case, let's suppose we reach the maximum frequency at some point. After that point, the frequency will immediately drop off to Fc minus Bw by 2. And after that, the frequency will gradually increase again, and finally it will reach a frequency, instantaneous frequency of Fi, which is the same as the starting frequency. So basically, we will start with an instantaneous frequency Fi, gradually increase the frequency until we reach a maximum of Fc plus Bw by 2. Then instantaneously we will drop off to instantaneous frequency of Fc minus Bw by 2. From there we will start increasing the frequency again until we reach an instantaneous frequency of Fi, which happens to be our starting frequency. So if we see the total range of frequencies that this CSS signal traversed, it should turn out to be exactly equal to Bw, which can be easily verified because over this range there is a frequency sweep of Fc plus Bw by 2 minus Fi, and over this second range there is a frequency sweep of Fi minus Fc minus Bw by 2. So if we if we add up these two frequency ranges, that is this quantity plus the quantity down below, we will see that these two add up to exactly a value equal to the bandwidth. So this is how a chirp signal, no matter what its starting frequency is, it will traverse or sweep over a frequency range exactly equal to the bandwidth of the signal, and the center frequency will turn out to be exactly equal to Fc. The question that arises now is, what are the starting frequencies, Fis, of different possible chirps? As we know, CSS is an M-array modulation format. So that means we will have M possible chirps. And for each chirp, our length or the duration of a chirp is the same. So a chirp will always be of the same duration regardless of which modulation symbol we are talking about. So under these circumstances, the only way to differentiate between two chirps is to vary the instantaneous initial starting frequency, the starting point of a chirp. To exactly quantify this Fi, let us first define a quantity called spreading factor first. Let's call it SF. This is a key parameter of the CSS scheme. SF is actually nothing but number of bits per CSS symbol. So what we mean by that is every CSS symbol will pack in SF number of bits, and that translates to the statement that M is equal to 2 to the power SF. So we have an M-array modulation scheme of which each symbol is carrying SF bits. So SF is nothing but log of 2 M. So the spreading factor is the key parameter, and it has taken quite a foothold in the literature on IoT and literature on LoRa, because LoRa defines its signal characteristics almost purely in terms of the spreading factor. Thus, to sum up, we have M is equal to 2 to the power SF modulation symbols, each having a different starting frequency Fi, and each symbol having the same time duration given by tsim. The value of the symbol duration tsim is given by the modulation order M, which is also equal to 2 to the power SF, divided by the bandwidth. So there is another term known as chirp rate associated with CSS modulation. The chirp rate is given by mu is equal to bandwidth divided by tsim. So it's clear that the chirp rate is essentially the rate at which the instantaneous frequency changes, because we know that the instantaneous frequency spans a range of, or sweeps a range equal to bandwidth over a time duration of tsim. So this can also be expressed with a little bit of manipulation by bandwidth squared divided by the modulation order M. And it's clear that its unit would be hertz per second. So this says that over the same bandwidth, if we keep the bandwidth the same, the chirp rate would decrease linearly with the value of M. Whereas if we keep the modulation order M the same, then the chirp rate will increase quadratically as we increase the bandwidth. And one important thing to keep in mind here is that different choices of bandwidth and the modulation order can still lead to the same chirp rate. So in order to completely characterize the CSS modulation, we need to characterize any two of these. So either we have the bandwidth and M, or M and the chirp rate mu, or mu or M the bandwidth. So if we can characterize, specify any two of them, then we have completely specified the CSS signal set. Of course, provided we also know the center frequency FC and the bandwidth of course we know the center frequency FC. Let us now try to get mathematical expressions or derive mathematical expressions for different chirps used in the CSS modulation format. Of course, there are M such chirps. Our representation will be in the complex baseband domain. So we will be using the complex baseband representation of the chirps. As we all know, from the complex baseband, we can go to the actual passband signal by simply multiplying the complex baseband representation with a complex exponential. Now, before going to the complex baseband representation of different chirps, let us consider one specific chirp. As we know, the chirps are defined by their starting frequencies. So we would be looking at a very special chirp, which is called the basic chirp. And its speciality is that it starts at the lowest possible frequency fc minus bw by 2, and of course it has to go all the way to fc plus bw by 2, because every chirp will have to span a total range of frequencies whose bandwidth is bw by 2, and that has to be done over a period equal to t sim. Now this basic chirp, if we consider it in the baseband, then we will have to make the value of fc is equal to 0. Then the basic chirp is dragged all the way down to the baseband. So in the baseband, the complex baseband representation for the basic chirp is given by, we write it as x naught t exponential j 2 pi mu t by 2 bw by 2 multiplied by t, and this time axis t goes from 0 to t sim. So just to remind ourselves, this mu is the chirp rate, and bandwidth of course is the bandwidth. So it is easy to see that when t is equal to 0, we have an instantaneous frequency of minus bw by 2, and when t is equal to t sim, we have an instantaneous frequency of bw by 2. So this chirp, this complex baseband representation, is for one of the possible chirps known as the basic chirp. This chirp is also called the symbol 0, because each chirp represents one symbol. We are talking about the symbol 0, which represents the all 0 symbol. Since we have called the basic chirp as x naught t, let us write all m symbols as x naught t, x1 t, all the way up till xm minus 1 t. So this x naught t is the basic chirp, and the symbol x1 t is the chirp number 1, or we call it the symbol 1, whereas basic chirp is symbol 0. This is symbol 1, and so on. So from here, how do we find x1t through xm minus 1t? The idea is to take the basic chirp, then we shift it in time, shift it cyclically in time by amount m delta t, where delta t is equal to 1 by bandwidth. So if we do this shifting, that gives us symbol m. So essentially, we have a basic chirp, and each of the other symbols are cyclically shifted versions of the basic chirp. Symbol 1 is obtained by shifting symbol 0, cyclically shifting symbol 0 by an amount equal to delta t, where delta t is equal to 1 by bandwidth. Symbol 2 is obtained by cyclically shifting the basic chirp by an amount to delta t, and so on. Mathematically speaking, then, we can write the mth symbol xmt, its complex baseband representation, as x naught mod t minus m delta t comma t sim. So the modulo operation with respect to t sim gives this cyclical shifting, since each modulation symbol will have a duration of t sim. We write 0 to tsim. And of course here m, the symbol number, can be anything between 0 to capital M minus 1. So this is the complex baseband representation of the M signal, M symbols, of which are all represented in terms of the symbol 0 x naught, and x naught's expression is as we just discussed. Now it can be mathematically shown with some manipulation that all these symbols are orthogonal to one another. So it's an orthogonal signal set. So we will not write down the derivation, but just to reassert the idea of orthogonality, we will write 1 by tsim if we integrate the product of any two CSS symbols. These are complex baseband representation. That is why we have a complex conjugation. If we do this, our result will be written as delta m minus n. Actually, this is a Kronecker delta function. That is saying that this result is 1 if m is equal to n and 0 otherwise. So this is the orthogonality of these modulation symbols that is allowing us to transmit SF bits or 2 to the power SF symbols without having one symbol interfere with the other. Having defined the CSS symbols, let us now check what happens if we try to get a discrete sequence of samples by sampling the continuous time signals that we have just discussed. The reason we want to look at the sampling of CSS symbols is because that leads to a very simple form of CSS demodulation. First of all, let's recall that the bandwidth is BW. Bandwidth of the entire CSS signal was BW. In the passband, it goes from FC minus BW by 2 and FC plus BW by 2. In the complex baseband representation, it goes from minus BW by 2 to plus BW by 2. So this complex baseband signal, since its maximum frequency component is BW by 2, then sampling theorem states that we can sample the signal at a rate f sample equal to BW without losing any information. That means we can perfectly reconstruct the CSS signal by taking samples at a rate of BW. Now, if we do sample the signals at the rate of BW, f sample is equal to BW, then what do we get? For that, let us first check what happens to the basic chirp or the symbol 0. So let's consider the sampled version of the symbol 0. So this is nothing but x naught of t, where t we have discretized by taking n times t sample, which is equal to n BW inverse. So that can be written as, by invoking what we wrote in the previous notes or previous slides, we can write this as n BW inverse divided by 2. We have simply substituted the parameters mu, and instead of t we are writing n times t sample, or n by bw. So this is the expression we get, which can be further simplified. So let us try to simplify it. Upon simplification, it turns out that x naught n is equal to exponential j 2 pi n squared by 2m minus n by 2, and this time index n goes from 0 to 1 to m minus 1. This can be easily seen from by first noting that the original continuous time in time parameter went from 0 to t sim, and then we were sampling these at a rate equal to bw. So it follows upon inspection that the discrete time in the instance n goes from 0 to all the way to m minus 1. So it is saying that there are m minus 1 total samples that we get. But here the important thing to note here is that this expression that we see here is independent of the bandwidth parameter. So there is no bandwidth parameter anywhere. All we see here is the parameter m. So that is saying that the sampled versions, or the sampled version of the discrete time basic CSS symbol, it depends only on m and not on bandwidth. So there are, so we can write down the some important properties of this sampled version. So first of all, it depends on m alone. Number 2, it contains m is equal to, which is nothing but 2 to the power sf complex samples. Then we can also see with some manipulation that the mth symbol, if we sample it at the same sampling rate, that can be written as x naught mod n minus m comma capital M. So it is saying that even in the discrete time, the sampled version of the mth CSS symbol is this cyclically shifted version of the sampled basic signal, basic symbol, or basic chirp, or symbol 0, however we wish to call it. In fact, with some manipulation, it is very easy to see that the mth sampled symbol is equal to the 0th symbol plus m. So there is no modulo operation actually needed. So we have a very simple expression for the mth sampled symbol in terms of the basic symbol. And finally, even in the discrete domain, all the discrete time chirps, discrete time symbols, are orthogonal to one another. So we still have orthogonality in the discrete time domain, and that is expressed as 1 by m, and from 0 to m minus 1, x of mn times xk n is equal to m minus k. So this is an important property in terms of the way CSS symbols or CSS signals are handled in the discrete domain, that we have our orthogonality preserved in the discrete domain as well. So these properties, the reason we discussed them was because in most implementations of CSS in the practical world, especially for LoRa-based devices, the demodulation would most likely be done in the discrete domain. And that is what we would discuss next. So let us now look at the demodulation of CSS. In particular, the type of demodulation we will be discussing is known as DFT-based demodulation, which is done in the discrete domain, as I mentioned, using the sampled versions of the CSS signal. So to get started, we will consider a AWGN channel. So the received signal, if we send the symbol x of m, the mth signal, would be the signal itself, the transmitted signal, plus a noise component. So this xmt is the transmitted symbol, and this WT, the noise component, since we are considering an AWGN channel, what we have is a complex Gaussian noise waveform. We will assume that that is power spectral density is equal to n naught. Now this is the continuous time representation, which is what would be available at the output of the receiver antenna. Here, remember, we have assumed that the channel attenuation is 1. That is, the transmitted signal is not attenuated, which of course is a special case, but there is no loss in generality in assuming so, as long as the channel is AWGN. If the channel is not AWGN, then of course we will have certain fading coefficient multiplied with the transmitted symbol, but that is not within the scope of today's discussion, so we will exclude that. Now, once we receive this signal, the next step is to sample it. So if we sample the signal RT with the sampling duration B is equal to BW, sampling frequency is equal to BW as discussed before, then we obtain R of n, the sample values of the received signal, as the sampled values of the transmitted symbol plus the sampled values of the noise. And we had already seen that the time index n takes on a total of m values, 0, 1 to m minus 1. Now the DFT-based demodulation is based on the observation that if we take any chirp, x of m n, and then multiply that same chirp with the complex conjugate of the basic chirp, then this gives a sinusoid of constant frequency. So to see this, let us call this signal Vm of n. So this multiplication, we can write this based on our earlier derivation of the sampled versions of different chirps as j2 pi n plus m whole squared by 2m minus n plus m by 2 minus n squared by 2m plus n by 2. So this follows from by applying some mathematics, some manipulations to what we have already mentioned in previous discussions. And this further simplifies to j 2 pi m squared by 2m minus m by 2 multiplied by another exponential. So we have essentially separated out two exponential signals. Here what we have seen is that this first multiplicand, this has no dependence on n. So this is independent of n. So n is the time instant, and this first term does not depend on n. So this implies that this is nothing but a constant phase multiplier. On the other hand, the second part, this is exponential j2 pi m by n times small n. So this is essentially of the form is nothing but a sinusoidal signal. So this is a discrete time pure sinusoidal signal. There is only a single frequency. And this forms the basis of the demodulation, as we will see in a moment. Okay, so it will be beneficial to write down the expression once more. So Vmn, which is xmn times the complex conjugate of the basic chirp, that is the phase term, which is j2 pi m squared by 2m minus m by 2 times exponential j2 pi nm by capital M. So as we just discussed, this is a constant phase term, the first term, but the second term, this pure sinusoid, this has a frequency small m by capital M cycles per second. Now let us see what happens if we take the DFT of this Vmn. So let us try to take the DFT and write it as Vmk. So we have written this. This has a total of m points, since n goes from 0 to m minus 1. Now let's take this sequence Vmn and take an m point DFT, and that gives us n from 0 to m minus 1 Vmn exponential minus j2 pi nk divided by m. So this is the DFT equation, and the expression simplifies to j2 pi m squared by 2m, which is just the phase term from the Vnm expression before, multiplied by n from 0 to capital M minus 1 exponential j2 pi n m minus k divided by capital M. and k goes from 0 to m minus 1. So this is the straightforward DFT expression after some manipulation. Now, if we look at this expression and then try to simplify, it's actually not hard to see that the answer is capital M times exponential j 2 pi m squared by capital M, 2 times capital M, sorry, times m by 2 if we have k is equal to m. And if k is not equal to m, then we have a result of 0. So this is telling us that if I take Vmn, which is the multiplication of the transmitted chirp, the mth chirp or mth symbol, multiply that with I'm sorry, to repeat, if we take the value of Vmn, the sequence Vmn, which is the product of the mth chirp and the complex conjugate of the basic chirp, and then take its DFT, m point DFT, we will have a result in which the m point DFT will be having a non-zero value at only one value of k, and everything else would be 0. And that non-zero value would occur for the value of k equal to m. So that means if I take if I am transmitting the mth chirp, so chirp, let's say I'm transmitting symbol number 4, and then if I do this DFT procedure, eventually I'm going to end up with a sequence DFT output whose value will be 0 everywhere except for the 4th symbol. So to see how CSS demodulation would work, let us again consider the reception of a signal or the sampled version of the received signal when the transmitted signal was the mth CSS symbol. So let us for the moment assume that this omega n is 0, and then we will include this effect in a moment. But for now, let us suppose we have a channel where there is no noise. That means the noise sample value is always 0. Then take this signal R of n and multiply that with the sampled version of the complex conjugate of the 0th symbol or the basic chirp. So that would give us xmn times x0n. But this quantity is nothing but the quantity Vmn that we just considered. So if we do this and then take the DFT of the product, this is equivalent to taking the DFT of Vmn, which we just found out to be Vm of k, and that was found out to be a non-zero value. I'm skipping the terms inside. A non-zero value if k is equal to m and 0 otherwise. So what it says is that if I am receiving a CSS symbol over a noiseless channel, all I have to do is multiply the received signal by the complex conjugate of the sampled version of the basic chirp, and then take the m point DFT of the product, and then look for the DFT index for which we get a non-zero value. That DFT index k will correspond to the number of the symbol that was sent. That would be the mth symbol. So we would look at the final DFT output. The DFT output will have total M samples, of which, let us say, sample number 2 is non-zero and everything else has to be 0. So in that case, we would declare that the second symbol or the second chirp number 2 was sent. So this is how the DFT-based demodulation of CSS would work in a noiseless channel. Now, if the channel has noise, then also the same thing applies. There, we cannot say for sure which symbol was sent, but instead, we are going to take do the same steps. We will multiply the received signal with the complex conjugate of the basic chirp, and then take the DFT. And whichever DFT sample has the highest value, has the maximum magnitude, that particular index, the index of that sample would be declared as the transmitted symbol. Thus, to formalize our demodulation procedure over the AWGN channel, we can write that the received signal R of n is the transmitted symbol xm of n plus the noise sample w of n. Then we would multiply R of n with x conjugate of x naught conjugate of n. That would give us x naught conjugate of n xmn plus wn times x naught conjugate of n. Then we will take DFT of both sides. Here, the DFT of this quantity will give us the VMK that we just saw, and let us denote the DFT of the noise sequence times the x naught conjugate n sequence as W of k. Of course, W of k has no dependence on the term m. So since we already know the expression for VMK, which is non-zero for k is equal to m and 0 otherwise, we can simplify this complete expression as m times exponential j 2 pi m squared by 2m minus m by 2 plus w of m. I'm sorry, this has to be w of k. And otherwise, it's going to be w of k. So it is telling us that the final DFT sequence that I will obtain is, suppose this mth sample was sent, mth symbol was sent, then this mth symbol will have some mean, a value with certain mean and a certain variance. Well, all other samples would be zero mean values because this quantity wk is a zero mean random variable. So each of these zeros and ones and twos will have certain zero mean value, but eventually we would, these are all zero mean complex values. So eventually we would take the magnitude of each of them and then find which of these samples has the highest magnitude. So if the mth sample has the highest magnitude, then we would declare that xm of t, the mth chirp, was sent. So of course now, due to the presence of noise, sometimes these noise components might have large enough magnitudes so that we get the incorrect result. However, since CSS, I mean, it can be shown that the probability of error with CSS is fairly resistant to noise. So we, in general, expect to get a fairly low probability of error. Of course, this error analysis we will skip because that is not within our scope. It requires probably another lecture. But overall demodulation technique is the process for the overall CSS demodulation in the discrete domain using the DFT-based approach is as we have just discussed. So combining everything, we can say that the receiver's estimate of the transmitted symbol number is the argmax of all the DFT magnitudes. So this y of k is the DFT of Rn. So this quantity, if we take its DFT, we get y of k. Just find the sample that has the largest value and consider that sample's location to be the transmitted CSS symbol. So this is our final CSS demodulation procedure on an AWGN channel, of course. If it's a fading channel, then we would have the receive symbol equal to some fading coefficient times the transmitted samples plus the noise. So there we have to do some type of equalization. So for example, we might multiply this received signal by h conjugate of n, assuming we have an estimate of h conjugate of n. So we will end up with something like this. And after this, the procedure is the same. We take the DFT and find out what is the maximum value of the DFT or the sample of the DFT that has the maximum value. So this is how we will demodulate a CSS signal. Now, while what we have discussed covers the modulation and demodulation of CSS, in a practical scenario, we need to take into account a lot of different attributes. We need to analyze them. So we will not discuss them here, but just to mention, one of the most important issues is that of interference. So interference, broadly speaking, this is the phenomenon when multiple signals are received at the same time. So multiple CSS symbols being received at the same time will interfere with each other. And it's possible that one of these signals will cause the loss of the other, or maybe all of them would be lost. So how interference works, that is very, very specific to the type of modulation and demodulation that is being used. So in general, what is found is that the CSS signals with different spreading factors do not interfere with each other significantly. So a practical observation with CSS-based modulation schemes, especially the LoRa modulation scheme, is that if we have multiple CSS signals, each using a different spreading factor, then they will not interfere with each other significantly. So there is a strong enough chance that we will be able to correctly decode a CSS signal, even if there are some other spreading factor interferers present. But then it has been shown that same spreading factors interfere severely. So if we have two CSS signals with having the same spreading factor, then there is significant interference. Also within the same spreading factor, it depends on what is the relative timings of the two signals. For example, are they aligning at the symbol boundaries or not? So there are many different issues that come into the picture, and it of course is one of the research areas that has been that is being pursued over the last few years, mainly driven by these LoRa applications. But the overall idea is that if two signals with the same spreading factor are interfering, then the interference is more as compared to the interference between different spreading factors. Then other issues that need to be specifically investigated is that of sensitivity. The receiver sensitivity, as we mentioned before, the lower the sensitivity, the better the reception. And as we already know, with CSS, the receiver sensitivity typically is much lower compared to many other modulation formats, leading to the CSS receivers or the LoRa receivers being able to receive signals at fairly low power level. And that is the main contributor to the fact that the LoRa communications happen at fairly low power as compared to many other communication techniques, such as the cellular communication techniques. So these are some of the basic ideas about CSS. So this particular talk was intended to be a very broad or basic overview of the modulation technique. We went through the modulation and demodulation in some detail, but all these additional topics, those are left for further investigation for whoever is interested. So I hope the talk was interesting. There are many papers on this issue, but a good starting point might be a paper by Dunlop and his co-authors. Its name is Interference Analysis for LoRa CSS signals. So although its name says interference analysis, it actually gives a very good overview of the modulation and demodulation techniques and then moves on to the interference part. So that makes it really interesting. So this paper came up in the conference known as the Canadian Conference of Electrical and Computer Engineering, abbreviated is CCECE. It's an IEEE conference. And the year was 2019. So whoever is interested, I suggest this particular paper as a starting point to understand the broad ideas behind LoRa modulation, demodulation, and interference. And then there is a long list of more advanced papers available. So I hope this talk was of some value. So thank you for giving me the opportunity. And I hope to see you again. Thank you.
Yeah, thank you, Dr. Siddhartha. So, dear participants, the previous speaker, Dr. Siddhartha, could not come live because his further expired suddenly one day before. So anyway, I can see a couple of questions from Kannan and Abhishek. So what you can do, I'll give you the mail ID of the speaker, so you can directly drop a mail to the speaker. Okay, and the next talk will start within 2 minutes, 11:15.